Yeah, first of all, thank you, Altinity, for hosting this amazing meetup, and thank you, Sentry, for this amazing office space. Really nice view. Hello, everyone. My name is Sida Shen. I'm a product manager at CelerData. I'm also a StarRocks contributor. And today I'm going to talk about Apache Iceberg, how to achieve data warehouse-like performance directly on Apache Iceberg. So first, let's go over the agenda. So first, we're going to talk about the original Iceberg promise, right? And why slow query is not going to only make a bad user experience, but it's also going to break the original Iceberg promise, which is better data governance, right? And then we're going to talk about challenges with good query performance on top of Apache Iceberg. Basically, all of the crazy bottlenecks we've run into in the past like 3 years, working with some of the biggest Iceberg deployments in the world. And then we're going to talk about how to fix your Iceberg tables first, right? What are some of the Iceberg features you should be using, and what are some of the maintenance jobs? What are some of the metrics that you guys needs to be looking at if you want really high concurrency, low latency queries on Apache Iceberg? And then we're going to talk about some of the engine side innovations. A lot of the features and optimizations we built that are very useful, to getting that kind of performance, right? And in the end, we're going to take a look at some real success stories from Apache Iceberg users. So first, right, Apache Iceberg, it is a huge step up from Apache Hive, right? It builds a lot of like great features like asset control, schema evolution, right? So you don't have to, list files, whatever you want to do. Actually, it has a pretty strong like metadata layer, right? So why are we doing that? Why are we building those data warehouse-like features on top of Apache Iceberg? The reason is, let's say you have some data that's stored in a proprietary data warehouse, right? With the format, the file and table format, is the proprietary format enforced by that data warehouse itself, right? So the amount of workload you can run on that piece of data is limited by the query engine, by the proprietary data warehouse, right? But if you, let's say, if you store something in Parquet files in an open table format, such as Apache Iceberg, you can basically keep a single source of truth data and run all of the tools you want, on top of that one piece of data, which is great, for data governance, right? It's really simplify your architecture, and it's very cost effective, right? So if it is really great, right? So our user actually doing this once data is in the Iceberg, they never leave, right? Or does it? Yeah, the reality is not really, right? Because queries are just not running fast enough, right? It's existing data lakehouse query engines that a lot of users are using today are not really built for data warehouse-like workloads, right? They're not really able to handle those demanding workloads, such as like customer-facing dashboards, very high concurrency, low latency kind of workload, right? Or it's caused by poorly maintained Iceberg tables, right? So users, they either over-engineer or overspend on their existing query engine to barely get passable performance, which is not really sustainable. It's not really future-proof, right? So as a workaround, a lot of the Iceberg users are forced to move their workload back to a high-performance proprietary data warehouse, just for query acceleration reasons. This does solve the performance issues, but it brings a whole new set of challenges and costs, right? So first, you have to consider the cost of actually maintaining a data warehouse, a proprietary data warehouse. Stateful use a lot of resources, right? Infrastructure level software is very expensive, very error prone, right? And then you have to consider the cost of actually the data ingestion pipeline, right? Not for a few ingestion pipeline, but for thousands of tables. That's a lot of pipelines to maintain, right? Writing terabytes, petabytes of files, from one format to another, use a lot of resources, really error prone, right? And then you have to consider, the challenge of matching the schema, right, a data type, and redesigning, the table indexes, data warehouse. That's a lot of work, right? And most importantly, you're breaking the original Apache Iceberg promise, which is one copy of data, right? One copy of data. You don't have to manage, same data scattered around in 15 different systems, right? That governance benefit, right? So now let's look at some of the challenges we've run into trying to achieve this kind of data warehouse-like performance directly on Apache Iceberg. right? So engine side bottlenecks, and data execution, right? So first, data access, right? So data fetch is quite difficult for Apache Iceberg, right? So first, the Apache Iceberg typically sits in a cloud object storage, something like AWS S3, right? So you would expect the response time to somewhere, in the 100 millisecond, right? Which is okay for what it is, but for query scanning, it's just not fast enough. For each query scan, we actually send a lot of scans. So if each one takes 100 milliseconds, it's not very good, right? And also, a lot of the Iceberg tables are not really well maintained, which means that they have a lot of small Parquet files just lying around in the S3 bucket, right? You have millions. We've seen millions of 1 megabytes, data file just lying around, waiting to be compacted, right? And compactions are always, they're not real time, right? And you end up with a random IO storm, right? And also a lot of the query engines built on top of Apache Iceberg or integrate with Apache Iceberg doesn't have a caching framework. So you're constantly hitting S3, right? You're constantly getting this kind of latency, right? And also, data files are not the only kind of files are there. There is, right, in Apache Iceberg. There are also delete files if you want to do deletes and updates, right? And for Apache Iceberg v2, delete files, they actually don't even have a one-to-one relationship, with the data file. So, yeah, so they're Parquet files. So every executor, so if you want to read the data files and delete file together, you end up, opening the same delete file over again, right? They're Parquet files, and you have to read the file, deserialize the file, and build a bitmap and merge that with, the file. It's very, very expensive, very expensive process to do. This is data access. After we get the data, right, we do query execution, right? A lot of the query engine that are integrating with Apache Iceberg, a lot of people are using this, such as Trino, right? They're built on top of Java, right? They're written in Java, right? So when they scan, it's based on rows, right? Very too little, vectorization or CMD they can use. So everything is row based. That's very slow, right? And also, when you do query execution, right? You want to do shuffling, in JVM. You use a lot of CPU, use a lot of memory. You run into GC problems, right? And that is a big challenge as well, right? And also limited parallelism. A lot of the query engines, including us, just a year ago, right? We use a single coordinator node to basically fetch metadata and do query planning, right? We use the coordinator nodes or not the entire cluster, right? That has a problem because actually reading Iceberg metadata is pretty expensive, right? So for most of the query engines available today, the execution is not really going to start until the entire planning phase is over. That sometimes takes even more time than the execution itself. I'll show a use case just in the next few slides, right? So pipeline stall, block any stage, anything that blocks the I/O, even the metadata reading, that's gonna block the entire cluster, right? So very limited parallelism. So metadata and planning, right? So this is the actual use case from a user that used Apache Iceberg. So they have around 300 columns, around 500,000, 500,000 new data files a day, right? And they, after compaction, after everything, they have around only 30 manifest files a day, each only 8 megabytes each, right? So only querying 1 month of data. Parsing metadata costs around a minute to do, right? And very high CPU and GC pressures during the planning phase, which is, the coordinator nodes. Scalability also hit a wall because even they scale the cluster to 100 plus execution node, it doesn't even help because it's not the execution that's the bottleneck. It is the planning, the query planning, right? So, okay. So yeah, so the timeline breakdown. For a lot of the users, over 80% of the query time is just spent, parsing metadata instead of actually executing the query, right? Query execution is fast, but planning is blocked by, manifest lists, reading the Avro files, deserializing the Avro files by a single node or very few nodes, right? Even small number of manifest files can cause very huge bottleneck because Avro files are just inherently very expensive to deserialize. and how to accelerate Apache Iceberg queries. Here are some tips, tricks, and best practices, right? So first, you have to keep your Iceberg tables ready, right? Apache Iceberg just operates like a data warehouse, right? So your normal data warehouse, like, tips and tricks, they still work, right? Best practice, they still work, right? Avoid data skews, right? Partition your data correctly, right? And use Apache Iceberg features such as hidden partition, right, to make your life easier, right? Watch for those like skews and hot partitions, right? Also, and also you have to do your compaction pretty regularly, right? You want to aim for something that's 128 to half a gigabyte, which is just a sweet spot for our query engine to read off the object storage, right? And also you want to don't forget to run minor compactions on the delete files, to merge those, to merge and rewrite those delete files, right, to make them fast as well. And also you have to carry your metadata too, right? You have to periodically rewrite your manifest, right? So merge the tiny ones to bigger ones, right? Also, you want to expire your snapshots. You don't want to keep like way too many snapshots, only like n days in versions only, right? And also you want to take a look at Iceberg v3, right? V3 just released deletion vector. That is a game changer, right? So instead of storing everything in Parquet files, we're now storing everything in a binary format with Puffin format with bitmap blobs, right? So when query engine read is so much faster, we can actually do SIMD read on the data files now, on the delete files now, right? According to the benchmark, it's around like 100 times plus faster read time, for delete files in V3. So definitely check out V3, check out deletion vectors, right? And most important, you have to choose the right engine, right? Right engine for the right job. You want to do ETL like job, or you want to do like customer facing, low latency, high concurrency kind of workload, different tools, right? And here I want to introduce StarRocks. StarRocks is exactly built for low latency, high concurrency like workloads on Apache Iceberg, right? It's a Linux Foundation open source project. It's purposely built, for those like data warehouse, like high performance kind of SQL OLAP workloads, right? Natively integrates with Apache Iceberg, open standard, file formats such as Parquet files, right? It has a really simple architecture with only two kinds of processes. So FEs are the front end nodes are the metadata planning, right? Metadata and query planning. And the CN nodes are basically our workhorse, right, for query execution. That's our MPP architecture, so fully distributed, written in C++, right? Also with StarRocks, you don't have to do denormalization because we gone through all of the miles, to actually make join fast enough to make them run on the fly, so you don't have to do denormalization for all of your data, right? And just to take a look at the performance first, so StarRocks versus Trino on TPCDS 1 terabyte. Is around 4.6 times faster than Trino on TPCDS, 1 terabyte. And this is even with Trino on JDK21, so supposedly have that auto SIMD thing, right? And okay, so this is the performance. And here are some of the optimizations we did specifically for Apache Iceberg, right? So first is distributed manifest scan. We know that manifest files are really, really expensive to read, right? And we have a bunch of CN nodes, and we're really good at doing distributed queries. So why don't we use the entire cluster to do that job, right? So that's what we did. So the planner is going to tell the executor, what to do, and the executors, so the CN nodes are actually going to go into the S3 buckets and read the metadata. And we read the manifest files. Come back with a file table for the FE, the cost-based optimizer, to actually come up with the query plan, right? And then we also built a metadata cache, which is both in memory and on disk, right, for all of the metadata tree of Apache Iceberg, right? We even cache some of the already deserialized manifest files, right, to make them even faster, right? And also has a ORU emission, policy, right, to make sure that the cache is always hot. So this is metadata handling and query planning, right? And then it's time to scan the data, right? To SIMD vectorized scan, right? So what we can do is SIMD scan basically is we scan not by row, we want to do them by batches, right? For OLAP, the more batch you run, basically the faster things gonna go, right? So we have column projection. So basically we know which column, to get, and also, predicate push down, for only the pages, target pages that we need, right? And, we decompress and decode, with SIMD instruction sets, right? So read, 4,096 rows per vector, right? And also we have optimizations on the scan operator, right? I'm not sure if you guys are familiar with equality delete files for Apache Iceberg. So that's basically a kind of update mechanism that is very fast to write, but incredibly slow to read, right? So basically, there are just equals the value, right, of the field that you don't need, right? So basically a soft delete. Um, um, Merging equality delete files and data files is extremely expensive process, right? So what we did, we figured out, equality delete and data file, that's basically a left anti-join, right? So instead of doing that on per node basis, we basically read all of the equality delete files and all the data files and do a big left anti-join, which is what StarRocks is best at, right? So basically to MPP this equality delete read process, right? To make this actually usable in production. So this is scanning, right? After scanning is query execution, right? Vectorized pipeline execution engine, right? So all of the operator within StarRocks, including scan, join, aggregation, source, run C++, right? So we say by vectorization, we basically means that in memory, instead of processing everything by row, we process everything by column, by small batches, right? That's vectorization, right? And also we have a push-based, optimizer that overlaps stages, right? That's pipeline execution engine. So we make sure there is no wait time, between each one of the pipelines, right? There's no, even the IO block is not gonna block the entire cluster, right? So what we end up with, is very busy CPU cores, right? And CMD can speed up, operators before we implement it and after, we see a 3 to 5 time, performance gain, right? And also we talk about the problem with planning, stalling the execution, right? We actually build something that's asynchronous. So when the plan is still running, we're still reading the manifest files. We're able to send fragments to the executors, right? So they can start working, right? So the planning doesn't even, block the entire process, right? This is just for Apache Iceberg. And also we have a cost-based optimizer that is built, to run high cardinality aggregations, right? To run multi-table joins to help you do join reordering, right? And also we have a runtime filter, runtime filter feature, which basically, when the join is still running, right, we're gonna decide if we send a Bloom filter from one table to another to prune the data, right? We calculate if that's worth it, to send the Bloom filter over to prune or not, right? We have optimization like this to make sure that every join is not processing the data that's not needed. Okay, so Iceberg and StarRocks in production, right? So this is WeChat. WeChat is a social media platform with 1.3 billion monthly active user, right? So their older architecture is based on the Hadoop-based data lake, right? And they have just a million different kind of data warehouses on top, right? With the same data copied just basically everywhere, right? And their requirements are crazy, right? They want to handle trillions of records per day, trillions of addition data per day, daily ingest, right? And their P90 latency needs to be less than 5 seconds, right? So before on this kind of scattered proprietary data warehouse plus Hadoop-based data lake system, they were juggling between multiple systems, right? And also they had a separated, real-time and batch analytics pipeline, right? And they were maintaining just many, many data ingestion pipelines for all of the data warehouses that they had, right? They were running into governance challenge, right? They were having a hard time keep up, with the data quality that they're looking for, right? Also, they were having challenges in standardizing data analysis process because for all of the tools that they're using, right, that was a really, really big challenge. And also data freshness was not good, using something like Hive. And then they switched to StarRocks and Apache Iceberg, right? They actually use StarRocks as like the OLAP cache layer. StarRocks actually has a like a optimized storage engine that you can actually ingest into. So columnar storage, 10-second data freshness, immutable data, right? So that's a in-memory kind of index that we use to accelerate the update and delete process, right? So they periodically sync their data into Apache Iceberg from StarRocks, right? So basically what they'd end up with was trillions of daily records and single source of truth on the Apache Iceberg with less than 10-second data freshness with mutable data, right? And they were able to consolidate everything into a single source of truth on Apache Iceberg. There are more StarRocks and Apache Iceberg success stories. If you're interested, take a picture, search them on Google, right? First is TRM Labs, right? This is customer facing. This was presented in Iceberg Summit 2025, right? Customer facing analytics, hundreds of terabytes of data, right? With a lot of complex joins and high cardinality aggregations on the fly, right? And they consider Trino, StarRocks, and DuckDB, and they pick StarRocks, and over their old proprietary system, BigQuery, they saw a lot of improvements, right? While running things in open formats. Second is RedNote, Iceberg Summit 2025 talk, 100 petabytes of historical data, right? And 3 petabytes of daily increase. This is crazy amount. This is probably the biggest use case I've seen. And they got like better than their previous proprietary real-time data warehouse like performance on Apache Iceberg plus StarRocks. And the last one is Tencent Games, right? So this is basically the same corporation as WeChat, right? So they presented this work, Iceberg Summit 2024, right? It's really fun. So PB scale Iceberg Lakehouse, with 10-second data freshness with StarRocks and Apache Iceberg. So this is actually all I have. StarRocks and Apache Iceberg get customer-facing like low-latency, high-concurrency queries directly on top of Apache Iceberg. If this sounds fun, join the Slack channel, right? Or scan the QR code. Is there any question? Yes. Yes, we do have Delta and Hudi support. Actually, the support is not that bad. Yeah, we build if we want to support something, we try to support all three altogether. But we tend to do Iceberg first and then Delta and Hudi together, or Delta first and then Hudi. Or depends. It really depends on the use case, right? The table formats are kind of similar. Especially with Delta and Iceberg, right? They're getting like way too similar to some extent, right? But for Hudi, it's a complete different kind of use case, and Pyman also, right? For like real time, more like better data freshness, right? So different purposes, different features goes into different kind of open table formats. That makes sense. Any question? Thank you. Appreciate that. Thank you.